Near the city of Geneva, Switzerland, there is a tunnel.
It's this huge tunnel, over 100 meters underground and 27 kilometers long.
How the particle accelerator altered the weight of one electron and therefore destroyed our universe and shifted us into the universe that's directly next to it, and therefore things are different in this universe.
To many people, the Earth below France and Switzerland is solid and tranquil. However, based on the recent happenings in one of the biggest inventions by humans, located meters deep under these two European countries, it is anything but peaceful. Eminent scientist Roger Penrose has reported that some scientists and researchers have claimed a lot is going on at CERN, and nobody can give a full explanation yet.
To be understanding something, you need to be aware of it. And to be aware of it, you're conscious of it. There's something else going on.
What is going on at CERN's LHC facility? And why is it freaking everybody out? Stay tuned as we bring you Roger Penrose's warning that something evil just happened at CERN that no one can explain.
They come through there, from there, and they go into the center of the detector where they collide with the beam coming from the other side.
Few guests on Joe Rogan's show are more esteemed than Sir Roger Penrose, whose name is synonymous with amazing discoveries in both fields of mathematics and physics. His high-flying career is littered with celebrated achievements. Penrose is a recipient of the prestigious Nobel Prize in Physics for his groundbreaking work on black holes. His work on black holes confirmed what the general theory of relativity predicted about the monster structures. Penrose's work was in parallel with the late Stephen Hawking, with whom he developed the Penrose-Hawking singularity theorems. They formed the mathematical basis for the existence of singularities and the event horizon. This singular work opened up a vast knowledge of space-time, and it was enough to earn him the prestigious Wolf Prize in physics.
Well, first of all, I had a theorem about black holes, and Stephen Hawking picked up on this and showed this applied to the universe as a whole as well, and that the singularities were completely general.
Penrose's intellectual strides go beyond the cosmos. He also co-developed the Moore-Penrose inverse. This is a concept that has become very crucial to algebra, which has diverse applications in many scientific fields. Penrose also came up with the Penrose tiling. This is a non-periodic tiling pattern that continues to confound mathematicians and artists. This science titan is a recipient of the highest award issued by the Royal Society, the Copley Medal. Other awards he has earned include the Eddington Medal, the Royal Medal, and the Albert Einstein Medal. Penrose has had the honor of his theoretical work being the basis of many experimental pursuits at CERN, helping scientists who are probing the fundamental particles and forces of the universe. For example, CERN's Large Hadron Collider, or LHC, measures scattering amplitudes which are closely related to some of the abstract ideas formulated by Penrose. Penrose proposed the Orchestrated Objective Reduction, or ORCH-OR theory. This theory proposes that quantum processes are important in the development of consciousness. It acts as a bridge between physics and the mind's philosophy, and Penrose's books go into details of these challenging and complex subjects. Penrose's theory of conformal cyclic cosmology also offers a cyclical approach to the universe. Every single iteration or eon beginning with the Big Bang theory is a fresh and radical take on where everything came from. CERN, which stands for the European Organization for Nuclear Research, was established in 1954. It is a hub of scientific research that seeks to illuminate the very essence of the universe. One of the biggest achievements of the CERN is the discovery of the Higgs boson particle. It was a very sought-after particle that many researchers spent their whole life chasing. However, the breakthrough came in 2012 at the LHC facility. The Higgs boson is sometimes called the GO particle. It is one of the fundamental particles whose existence was theoretically confirmed by the Stand model of particle physics. Scientists used the existence of the Higgs boson particle to explain the way other particles obtain their own mass.
And today, actually, the beam turned for the very first time again in the LHC at injection level, so not yet accelerated.
If this particle was not confirmed, the almighty Standard model would have forever remained incomplete, like a puzzle without the last piece that ties everything together. In addition, the Higgs boson particle opened up new pathways for investigating the beginning of the universe. However, without the LHC, it would have been near impossible to discover the Higgs boson particle. The LHC is a massive ring-shaped structure that is 27 kilometers in diameter. It is buried under the soil of both Switzerland and France. It is like a humongous racetrack where scientists race particles at very high speeds before smashing them together. The construction required cooperation among countries with a hefty price tag that ran into billions of dollars. It is a busy hub of activity where scientists from more than 100 countries run experiments. The purpose of the LHC is to investigate the fundamental building blocks of the universe. But where does the smashing of particles come in? Here is how it works. The massive magnets in the LHC accelerate particles and guide them inside the ring. As the speed increases, the energy of the particles increases. The particles are then made to collide head-on at 4 points in the ring. There is a release of a huge amount of energy when this collision happens. What is interesting to the scientists is the resulting debris from the impact. To be able to study the debris, the LHC has enormous detectors, including ATLAS and CMS. They are positioned near the collision points where they can capture the aftermaths of the collision. This is how new particles and interactions or forces are detected. Even though the particles colliding are tiny, the amount of data generated and captured is massive. Trawling through this data are giant computer grids, helping scientists to sift through petabytes of information. Sometimes, they find evidence of the occurrence of events that could change everything that we thought we knew about the universe. Millions of people go about their business daily in Switzerland and France without an inkling of what is happening beneath their feet in the LHC. The LHC's magnet, for example, contains magnets that are cooled to temperatures lower than outer space.
Order of negative 450 degrees Fahrenheit.
Is that colder than outer space?
That's colder than outer space.
Oh, it is?
Yeah.
These cold temperatures allow the superconducting materials of the magnet to create powerful magnetic fields that accurately guide the particles. There are also the LHC's vacuums, which are said to be emptier than the emptiest vacuums in the universe. They have to be to prevent the racing particles from colliding with air molecules, which will cause them to lose energy. The accuracy of the LHC is such that it can focus a beam of protons that are thinner than human air. And this may blow your mind. The LHC generates an astounding 40 terabytes of data per second during a collision. The particle accelerator uses a sophisticated algorithm to filter out the noise to give scientists a better chance of spotting rare events. And how does the LHC mimic the conditions at less than a microsecond after the Big Bang? Let's start by imagining a pot of hot, dense soup where quarks and gluons swim. These are the particles that would eventually form protons and neutrons that make up the atom. This quark-gluon plasma is exactly what the LHC recreates. When particles accelerate to near the speed of light and are smashed together, it is actually history being made all over again. This type of collision produces temperatures of over 1 trillion degrees Celsius. These are hotter than the center of a supernova. Even though this state is fleeting and quickly passes, it is very similar to the state of the early universe. But the LHC does much more than reenacting the Big Bang. Sometimes, scientists use it to smash together heavier ions. These could be lead. When this happens, the heavier ions are pressed flat into disks due to what is called the Lorentz contraction. These types of collisions produce even more power, generating a fireball of quarks and gluons. Some of the findings by the LHC have provided more insights about quark-gluon plasma, including some that caught the scientists totally by surprise. For example, the facility has let us know that the plasma acts like a perfect fluid, having virtually no viscosity. By the way, the entire universe was once filled with this plasma. The functions of the LHC detectors are very complex. In fact, each of these objects is a marvel of modern engineering, and we tell you why. These detectors help scientists track and identify a multitude of particles that result from the collisions of particles around the speed of light. The design of these is like a very complicated camera, which they basically are. They capture photos of the particles immediately after they collide. The LHC's primary detectors are the ATLAS and CMS. They are general-purpose detectors used to probe many and varied physics concepts. They are a combination of multiple high-tech innovations, with each subcomponent dedicated to different types of particles. There are inner systems closest to the collision point. that accurately record the charged particle's path. This later enables researchers to reconstruct the path taken by any of the particles. It can lead to the inference of new particles. The inner tracking systems are surrounded by calorimeters used to measure the energy on a particle by absorbing it. Then there are outer systems that solely detect muons. These particles are special because they can easily escape through the inner layers or systems. Fun fact is that each of these detectors weighs more than the Eiffel Tower. The size, however, is not the most shocking thing about these objects. Did you know the CMS detector uses about 75 million structures? Each of them has to be finely tuned to track the particles passing through. The degree of precision is critical because the dimension where everything is happening and the observation is being carried out is smaller than an atom, and the time frame is just a fraction of a second. You literally can't afford to blink. Another detector is the LHCb. This one is dedicated to unraveling the differences between matter and antimatter. It is special because it is used to measure the properties of particles containing beauty quarks. Beauty quarks are among the heaviest and most complex quarks known to scientists. It is worth noting here that without innovative data analysis techniques, all these humongous and sophisticated machines will be completely useless. This is because when two protons, for example, collide inside the LHC, the collision produces many particles. These particles, in turn, collide with one another, resulting in about 1 billion collisions per second. The data generated is out of the world, and handling the information is a Herculean task. To accomplish this, scientists use complicated algorithms to comb the overwhelming amount of data. Scientists these days also apply machine learning to make sense of the huge data dump. The aim is to tease out interesting events from all the subatomic chaos that could signal new physics. This arduous process was how the Higgs boson was discovered. The Holy Grail would be the confirmation of dark matter. Further complicating this step of the experiment is the need to calibrate and align the data. This is required to ensure accuracy and account for some variations. For example, the scientists have to account for the different responses coming from different parts of the detector. They also have to account for changes such as temperature and magnetic field variations. They would then combine everything in the next step of mapping the particle's path and confirming their identities. Probability comes into play here. Because large amounts of data are involved, the observations in this type of experiment are subjected to the laws of probability. What the researchers are doing is trying to pick out signals from statistical background noise. Have you ever tried looking for a needle in a haystack? And here is where it gets complex. For a physicist to announce a discovery, they must achieve a certain level of certainty, usually referred to as 5 sigma, which means the event has only 1 in 3.5 million chance of being a fluke. To achieve this certainty level requires high-level statistical techniques and a deep understanding of theoretical predictions, combined with a knowledge of the inner workings of the detectors. One tool that has helped scientists working at the LHC is data visualization. It allows researchers and the general public to conceptualize or form imageries of the highly abstract and complicated interactions occurring at such tiny scales. They use graphics to illustrate the collisions and the subsequent trajectories of the debris. It is incredible that scientists can work out the properties of these particles, such as their mass, momentum, and energy. All these quantities are then compared to the standard model of particle physics predictions. The data processing power is another modern marvel of engineering. It has to be powerful to be fit for the job. CERN's data center has about 470,000 processor cores and 11,000 servers operating non-stop. By 2018, the center had stored 300 petabytes of data. This is enough information to fill up 75 trillion pages of text. The CERN also controls the worldwide LHC computing grid, or WLCG. The global massive infrastructure integrates more than 170 computation centers located in 42 countries, just to be able to process the deluge of data coming from the LHC. The advantage of this arrangement is that scientists from all over the world can gain access to and analyze their experiment data. The pattern of how the LHC works is fascinating for most folks who do not work there. Every operational cycle of the facility is precise and meticulously planned. They call each of these segments a run. These runs are punctuated by long periods of shutdown for maintenance works. Each run usually lasts several years. For instance, Run 1 ran from 2010 to 2013, followed by a 2-year period before Run 2 ran from 2015 to 2018. During each run, the LHC works round the clock, with the exceptions being brief technical stops or winter stops for scheduled maintenance. Scientists try to cram as many collisions as possible into each run and gather all the data available to the last drop. However, the achievements recorded at CERN are much larger than the atomic scale. In fact, you might be shocked to learn the extent to which some of these discoveries affect your daily lives. Outside of tiny particles, one of CERN's most enduring and pervasive achievements is the World Wide Web. It was while British scientist Tim Berners-Lee was working at CERN that he suggested a system to make information sharing possible between scientists scattered across universities and institutes all over the whole. The system he developed was based on hypertext, which he also developed. The very first website in the history of humankind was hosted on Berners-Lee's computer. Since then, billions of websites have been created, revolutionizing how humans exchange information. CERN's contributions are also felt in medicine. The technologies used to detect particles can be imported into the field of medical imaging. The most popular example is the positron emission tomography or PET scan. It is now an important tool for oncologists diagnosing and monitoring cancer. CERN has also partnered on technologies used to improve cancer treatment using precise and efficient radiation therapy. Other advancements attributed to CERN include the use of superconducting magnets in medical imaging. Most people know about MRI or magnetic resonance imaging MRI scans, but don't know the technology behind it was originally developed for the magnets used in the LHC. In the LHC, the technology is used to direct particle beams, but it has been modified to make MRIs way more efficient. It has saved millions of lives by producing high-resolution images that help in early-stage discoveries of some cancers. Another beneficiary of CERN's work is the space industry. The extreme conditions required for the LHC to function have turned out to be a blessing for aerospace manufacturing that has sourced materials that can withstand the harsh conditions in space from CERN. The materials can function in extreme temperatures, exposure to high radiation levels, and other dangerous conditions. Meanwhile, it is not always a jolly time at CERN's LHC as things can get scary in this massive underground facility. One of the scariest and most talked about concerns is the possibility of the scientists creating a black hole. According to theoretical physics, the LHC could be capable of producing the energy density necessary to make a black hole. Why would scientists at the LHC want to create a black hole? The reasoning is that if they succeed in creating a black hole, it could help them gain insights into how gravity and quantum mechanics behave at very small scales. Meanwhile, scientists have tried to reassure the public that there is no danger from the black holes. They claim that if these black holes form, they won't last because of a process known as Hawking radiation, which involves black holes emitting radiation and losing mass and energy until they vanish. They even claim the black holes will evaporate almost instantly. They also claim that the cosmic rays striking the planet impact far more energy than what could be generated by the LHC. However, what if something goes wrong like we always see in the movies? What if the black hole does not evaporate, but continues to grow and consume everything around it like black holes are known to do? Popular podcaster Joe Rogan has talked about these concerns on his shows with some of his guests. He has used his large platform to extensively discuss the risks of exploring unknown territories in physics, even though experts tend to write off his opinions as those of a layperson. There is also the aspect of quantum mechanics that has given experts more than a few sleepless nights. Quantum mechanics deals with subatomic particles. The difference here from classical physics is that the traditional laws of physics do not apply. You can have particles existing in multiple states simultaneously with behaviors that are not deterministic, but probabilistic. An intriguing offshoot of quantum mechanics at CERN is the many worlds theory. This theory proposes that all alternate histories and futures are real. Each history and future, whether alternate or not, stands for a world or universe. CERN experiments involve smashing these worlds together to extract their fundamental components. The speculation is whether the particle collisions at LHC can affect or reveal these many worlds. While all these remain philosophical and theoretical, it has become a hot topic among scientists and researchers alike. Opening our eyes to the possibilities of CERN's LHC is Max Laughlin. Laughlin might be young, but he is a prodigy. He has become popular in the scientific community due to his high intellect and his achievements. Laughlin got into quantum physics at the age of 9. While his peers gorged on cartoon shows and sweets, Laughlin would argue the fine principles of quantum physics with university professors. His inventions started gaining acclaim by the time he was 13, with interest from prestigious institutions like NASA and the Los Alamos National Laboratory. One of the things Laughlin has talked about is CERN. He has looked into the many potentials of the LHC, and what he has discovered is fascinating. For example, Laughlin has posited that using high-energy particle collisions, the LHC could produce a phenomenon that enables a gateway to other dimensions.
Particle accelerator altered the weight of one electron and therefore destroyed our universe and shifted us into the...
He based this on the theory that the energy produced during these collisions could be sufficient to reveal higher dimensions. The existence of these dimensions can be inferred from the string theory and other complex physics frameworks. Laughlin explains that these dimensions, which are outside of our own three-dimensional world, could become connected to our own world via tiny black holes. These quantum tunnels could also be generated during the collisions. Interestingly, Laughlin is all for creating these gateways as they will aid our understanding of matter from other dimensions. The sharp man is also looking forward to interacting with these dimensions through these gateways. He believes the interaction will broaden our understanding of the true nature of dark matter. Dark matter is a whole new world, yet to be explored, as it does not interact with anything known to humans. Laughlin is also excited about the possibilities of these other dimensions yielding technological advances that will floor everything that we have right now. For example, if other physical laws operate in these other dimensions, understanding the laws can help us drastically improve our energy production methods. It can also enhance our propulsion methods and revolutionize our computing capabilities. We would be able to leverage interdimensional states and properties to make our current technologies better. But by far more exciting and scary, depending on how you look at it, is the possibility of time travel. The concept of time travel has been around for a while, but has been confined to the imaginary world of films. But Laughlin points out the potential for time travel using these dimensional gateways. The concept of time might be different in these dimensions. This opens up the possibility of manipulating these time differences to move from the present to the past or into the future. He has also incorporated quantum entanglement, which involves particles being so connected that the state of one affects the other in real time. The amount of distance between them does not even matter. Could some of these other dimensions be connected to one another in this way? It may appear Laughlin is expecting too much from the LHC, but with the human mind's tenacity, who is to say anything is impossible?